everyone. My name is Johnny Raicu. I'm a senior at Glenbrook South High School, and I'm excited to talk to you all today about some of my summer research with Dr. Chard, in which we looked at improvements to accelerating the protein docking process and how we could make that process a little more efficient. But first, what is protein docking? So protein docking is a very complex process, very specific, in which a protein receptor and molecule ligand bind together. And because this process is very unique in that there's a very optimal configuration between the two pieces, it is computationally expensive and it also takes up a lot of time. And so one development that we've looked into is different machine learning models. And we've settled on the K-nearest neighbors machine learning model to focus on. And in the past, we've seen brute force approaches between one protein receptor and then many millions of molecules and testing these out one by one. And now with this, we've been able to reduce the search space entirely. And so our proposed solution is a Python-powered automated pipeline in which we integrate both Parsel to run certain tasks in parallel and machine learning to reduce the search space. And so with a data set of 4 million smile strings represented as those molecule ligands, so 4 million molecule ligands as these smile strings, we convert the smile strings into molecular fingerprints, and we also convert them into PDBQT files, which are the required file type for the docking process. And then from the docking process, we obtain a binding affinity score, which represents how optimal the configuration was between the protein receptor and the molecule ligand. And then we take the score and then the fingerprint, we pair them together, and then that is the input to our machine learning model. Once we've trained it and we've reduced the search space to the optimal 4,000, now we can run docking one more time, and that is one way we've created this more efficient process and pipeline. And then where Parsel comes in is in the conversions from the smiles to PDB to PDBQT. We've been able to integrate Parsel to run those tasks in parallel, as well as the molecular fingerprints. And so we've used Autodock Vina for our docking software, and then Visual Molecular Dynamics to visualize these simulations. And then we ran these simulations on 2 test beds, my 8-core personal laptop, and then a 192-core server. And then our total data set consisted of 4 million molecules. For a little kind of like inside sneak peek to what this looks like, a smile string is that chemical representation of bonds that a chemist might write. That's their notation. And then the software converts it into this more readable file type for the Autodock Vina. And that is what the Autodock Vina software utilizes. And so it did take a while to be able to get this conversion running. So over the summer, I think a few weeks was just learning how to make this conversion happen. And then once we got that running, we could focus on the more exciting part of the machine learning. And then this is an example of a docking output. We see that the docking score, the best one, is negative 6.36. And then these are other docking scores that come up. We want the most negative one because that represents the least amount of energy that it takes to take a receptor and a ligand together. And of course, we don't want a lot of energy being put into that process because that would mean that it's not a great fit. And then that's how much time it would take at the bottom. This is the distribution of docking scores. We look at the top 0.1% out of our 4 million. And so to the left of the green line, we classify those as the most optimal, the most negative 4,000 scores. And then we blow those up on the left. For the machine learning, again, we take the molecular fingerprint and our docking score, and we pair them together and feed it into the KNN, and then we train it, and then we get our new predicted docking score, not a smaller subset. And then one more time, these are just different ways to represent the same thing for different tasks. So we have the smile string, And that 2D representation is what a chemist might pair together. And then obviously a machine learning model like the KNN might not be able to understand that smaller string that a chemist might be utilizing. And so we convert that into a bit vector, and then that's a little more efficient because it's binary. And then we look at optimizing different parameters for the machine learning model. And so we settle on a fingerprint size of 128 and a fingerprint depth of 8. And that yields a 90% accuracy, which was fairly high looking at other works that have been done. And then our final performance and results, we achieved a 37x speed up on the server and a 38x speed up on my personal computer. And as you can see there, that block of yellow, that shows that docking really did take up the most compute time at 97%. And in conclusion, we were able to create a Python-powered automated pipeline using Parsel and machine learning to accelerate this protein docking process. And other applications include optimizing medications and drug design. And then even when COVID came around, if we had very efficient methods such as these, we could have more readily been able to tackle the virus when it came. And then I also submitted a poster based on this research, and it was accepted at IEEE SC 23. So I'll be presenting this in November at SC 23. And then this is some ongoing and future work. We're going to look at future machine learning models such as deep neural networks and consider different distance metrics for the KNN model. We used Euclidean distance, but looking back, because we used molecular fingerprints, which is binary, we could have used other distances, which would have yielded a higher accuracy for our machine learning model instead. Thank you.
Questions for Johnny?
Yes, Andre.
Do you plan to publish this tool on GitHub or something to make it available?
Yeah, all of my code from ParslDock is open source,
Okay.
so anybody could access it.
How about the tutorial? Already put together by others in the group.
Yeah, and the ParslDock was integrated in a tutorial as well at the Tapio workshop, and I think 40 students used it and learned from it, and so all of that is open to anyone who's interested in learning about ParslDock.
Yeah, like so too. Just a science question. Could you tell us about the receptor you were docking to?
The protein receptors, like what they are specifically, or
yeah, like what's the use case? What's the science use case at the end of the day for that receptor?
Yeah, well, we used a demo receptor, the 1IEP receptor, which isn't super significant in terms of the receptors that some scientists are using now, but in terms of the more significant use case, if you apply like the COVID receptor, then you could scale millions of molecules on that receptor and then look for the best molecule ligands which are optimal for that. And then you could tailor whatever you're looking for, you could change the protein receptor for that situation. Yeah, and I think there's around a dozen protein receptors which are very significant in different works. And then obviously we have many millions of molecules which are being used to be tested on these different receptors.
All righty then.
All right, thank you.